Okay. Hello, all. We are finishing up chapter 8, and this will be the last section for your exam coming up. So, chapter 6, 7, and 8. And I wanted to look at a couple more things to wrap up. Hopefully, I can do this in 2 videos. So, let's get started. I mean, 1 video, but maybe 2, I guess. So, this is an example. We talked about the last example we did in class. Was the problem how many elements of order 5 in Z25 cross Z5? And now this is asking, so it's taking it a little step further, find the cyclic subgroups of order 10 in Z100 cross Z25. So the process is similar to what we did in the last problem. We want to find the number of elements of order 10 because we're trying to find the cyclic subgroups of order 10. So first we need to find, so step 1 in this process is to find the number of elements that hashtag means numbers of order 10 in Z100 cross Z25. Okay. And so we can look at cases. I've already listed the factors of 100 and the factors of 25. So if we look at cases, the order of A, and then the order of B, and then case 1 would be A could be 2 and B could be 5 because we're looking for those two, that ordered pair, right? Because A, B is an ordered pair in Z, where A is coming from Z100 and B is coming from Z25. So A, in terms of finding those with order 10, those are the ones with the ordered pair, the least common multiple of the orders will be 10, right? And so when A is 2 and B is 5, the least common multiple is 10. Case 2, and if you want to pause this, you really can pause this since we did this part. You really can pause it and see if you can figure out the number of elements of order 10, and then we can move on from there. But case 2 is that the order of A is 10 and the order of B is 5. And then the last case would be the order of A is 10 and the order of B is 1. Okay. And so when you do that, you have the order of A. When the order of A is 2, that is 50. Okay. 50 is that only element. And when the order of A is, and that's using the method we talked about and going back in chapter 4 and remembering some properties, so you can go ahead and double check that. That'll be a nice review before the exam. For the order of A, B, and 10, the elements are 10, 30, 70, and 90 who have orders of 10. And when B is 5, those elements, when the order of B, I should say, is 5, then B is 5, 10, 15, or 20. And then when the order of B is 1, we have our identity 0. Okay. And so the total, looking at all the different combinations, the total number of elements of order 10 in Z100 cross Z25. Oh, I say cross because I'm used to doing your book. I'm trying to stay consistent with your book's notation, but when I'm used to doing the cross, the multiplication symbol for direct products, but I'll stay consistent with the book. Okay. So the total number of elements of order 10 in Z100 cross Z25 will be 24. 24 different combinations we can have. Okay. Now from that, we can sort of make this observation that and this you can sort of go back to chapter 4 to verify this, every cyclic subgroup of order 10 has 4 generators. And that's back, you can go back to look at this property here where we had something, it's like the cyclic subgroup of A is equal to the cyclic subgroup A to the K if and only if the GCD of 10 and K are 1. And so that means K would be 1, 3, 7, and 9. All right. Also, no two cyclic subgroups can have an element of order 10 in common. Okay, so there must be all right, so there must be 24 divided by 4, 6 cyclic subgroups of order 10 and Z100 cross Z25. So again, you may need to go back and review chapter 4 because again, chapter 8 isn't a new chapter. We're lumping together finite groups. And so if we're talking about finite groups, we're talking about cyclic groups. And so those properties need to come back into play. Okay, so now we're going to look at a theorem. We're going to prove this theorem, and I already wrote it just to save time in the video. So if you want to pause the video and write it in your notes, and then come back so we can go over it. Okay, so theorem 8.2 tells us that let G and H be finite cyclic groups, then G cross H is cyclic if and only if the order of G and the order of H are relatively prime. Okay, and so we're going to prove this. This is a biconditional proof, so we have to prove it both ways. And so we're going to prove it the direct way first. So let's assume that since we're given the fact that G and H are finite cyclic groups, let the order of G be M and the order of H be N. Okay, so the order of G cross H is M times N, right? That's just from definition. Assume G plus H is cyclic. Okay, so we're assuming it's cyclic. And we have to show that the GCD of M and N equals 1. Okay, so let the GCD of M and N equal D, some divisor, right? And let GH, the order pair GH, be a generator for G cross H because we know that it's cyclic. And so this is something where I told you all, this is, in theorems, you're not expected to just come up and develop, something that works. And this is something that takes years and years. It took mathematicians years and years to figure out. But we're going to take our generator and raise it to the Mn over D. Okay, so we're going to raise it to the Mn over D. And that's going to equal, just by properties of, because of how these cross products work or these direct products work, G to the Mn over D, comma H to the Mn over D, right? And we can rewrite these in this format here so that it equals, since the order of G and G is the generator for the big G, the group G, and a little h is the generator for big H in that sense, then they're going to equal E. And that subscript there is G, just to let you know that that's the identity in G, since that's first coordinate is in G, and that's the identity element H in the second pair. Okay, thus we can say Mn, which was our order of G cross H, is equal to, well, we know it's equal to the order of GH because that's the generator for that direct product. And we also just showed that M, if we raise that to the Mn over D, then that also equals the identity. But since Mn is our order, right, then that tells us, because the order representing the smallest power you raise to get the identity element, that tells us that that has to be less than or equal to Mn over D. Okay, and so thus D has to equal 1, because if D being positive. If it was anything else, then that would be smaller than m times n, right? And so that would negate the fact that mn is our order. Okay. Is it mn is the order of gh. Okay. Hopefully that made sense. Of course, take your time to marinate on that and go back over it. Let's look at the other way. So now we're supposing that the order of G, which is M, and the order of H, which we're still calling N, we're assuming that they're relatively prime. So the GCD of M and N equals 1. Now we have to show it's cyclic, okay? But let's not forget that we do have the fact that G and H are finite cyclic groups. So that means let G be equal to some cyclic subgroup generated by little g, and let H be equal to the cyclic subgroup generated by little h. Okay. If we take the order of GH, okay, then it equals the least common multiple, right? That's from what we talked about, equals the least common multiple of the order of G, comma the order of H. Well, that's just going to equal the least common multiple of M and N, because these are the generators for G and H respectively. And that, because we said, going back to the fact that we're assuming they're relatively prime, then the least common multiple of two numbers that are relatively prime will be M times N. And I don't know if we talked about that directly, but that's just a fact, okay? And so that equals our, the order of G plus H, cross H. So thus GH is a generator and it's cyclic, and we are done. And I thought that was a cool proof. Okay. Sort of summing up some things. Corollary 1, which is an extension of theorem 8.2, it tells us that an external direct product, so if we have sort of a group of finite, number of finite cyclic groups, so assuming that an external direct product, G1 cross G2 all the way to some Gn of a finite number of finite cyclic groups is cyclic if and only if the order of any two of those groups that you take, they're relatively prime when I is not equal to J. Okay. And corollary 2 says, let M be, let's say, some product of N1, N2, all the way up to some NK, then Zm is going to be isomorphic to Zn1 cross Zn2 all the way to Znk if and only if N sub I and N sub J are relatively prime when I doesn't equal J. Okay. And just looking at some sort of some examples. I don't know. I meant to do this, I think, earlier. Yeah, I wanted to do this earlier, but I didn't in the notes. So we're going to do it here because we're done with chapter 8 now. This is as far as we're going to go. I know there's some more applications and things. We just don't have time to cover that. So this is as far as we're going in the book for chapter 8. Okay, so find the order of each element. Let's look at A. 9, 18, and Z12 cross Z60. Okay, now this is still going back to chapter 4. So we're trying to find the order of each element, and it's the least common multiple of the order of the elements themselves, right? So we need to find the order of 9. I'll write it out for this one. The order of 9 in Z12. Okay, well, you may remember you take 12, so you take your mod and divide it by the GCD of your mod and the number, which 9 in this case. And so that's going to be 12 over 3, which is 4. So the order of 9 is 4. And then what about the order of 18 in Z60? Similarly, that's going to be 60 over the GCD of 60 and 18. And that's going to be 60 over 6, and that will give us 10. And so the order of 9, 18, okay, is the LCM of 4 and 10, which is 20. And of course, we're in Z12 cross Z60. All right. I want you to do these, and if you want to present them or ask me about them in class when we review, you can. So I want you to find the order of -1 and the permutation 1, 2, 3 in R star cross S3. C, find the order of 3, 10, and 9 in Z4 cross Z12 cross Z15. All right, and we are done. See you in class.